Okay, we're going to actually pick up with chapter 10 here, which is acid and bases. I believe with half of you there, I finished up chapter 8, which was solutions and discussion last week. For the other half, we will do it on Wednesday. The last couple of slides there from chapter 8, which was solutions, or 9, I'm sorry, from I think that was solutions. And so we're going to pick up here with chapter 10, which is acid and bases. And this is actually the sort of last chapter that involves really calculations before we kind of switch over to organic chemistry, which essentially will have no calculations. You really don't need a calculator for that part of the class. So we are getting into that sort of transition period there where we talked about at the beginning of the semester, where this is really sort of the last general chemistry sort of topic, which is acid and bases. And then we will transition in the next chapter into organic chemistry, which, as I mentioned earlier, is basically a little bit more memorization, a little bit more about some Lewis structures and drawing those type of things rather than sort of calculations. But I guess the good or bad news is this chapter does have a good number of calculations in it. So I guess we leave sort of general chemistry here with a good amount of calculations sort of involved. So let's talk a little bit about acids and bases here and just some of the general properties of acids and bases. Acids have a sour taste. Obviously, you shouldn't taste any acid or bases in a lab or anything like that. But things like citric acid, acetic acid, which is kind of like one of the components of vinegar. We are familiar with some of those things. They do cause litmus paper to change color. So oftentimes when we're dealing with acid and bases, we'll sometimes use what is referred to as litmus paper. And that is sort of that plant-based paper. And a couple of things to keep in mind, if you ever do use litmus paper, and for example, if you have red litmus paper and it turns blue, after you, for example, put a little bit of the solution on it, that indicates that the solution is basic. If you use blue litmus paper, which is another common sort of litmus paper, and you put your solution on it and it turns red, that usually indicates that it is acidic. So there's also neutral litmus paper as well, but basically, if your litmus paper kind of turns red, it means that the solution is acidic. If it turns blue, it does mean that it is basic. Acids do react with metals in a single replacement reaction, like we talked about in the chapter 7 chapter, I believe. Let me just sketch that there. So, for example, if you take a piece of zinc metal and you react with hydrochloric acid here, which is HCl, we get this single replacement reaction. Basically, the zinc comes in and kicks out the hydrogen. When it does so, it does generate hydrogen gas. So you see like bubbles, for example, when you do that. And we'll then make zinc chloride here. And we'll balancing for good measure, put a 2 there. But again, you probably maybe seen this or in one of those videos, especially with the chemical reaction, it's a very common one. You'll see a bunch of bubbles kind of come up as this reaction is taking place. Aqueous solutions conduct electricity. So if you have a strong acid, it's a strong electrolyte, which means it will conduct electricity. Bases, on the other hand, have a bitter taste. They feel very slippery. Lots of soaps are bases. Drain cleaners, for example, those guys are pretty much bases as well. They change litmus paper from red to blue. Again, that blue meaning basic, really. Also, strong bases will conduct electricity as well. And, a lot of strong bases do have hydroxide in it. So a lot of them do have OH minus in the formula, a lot of strong bases. And a lot of strong bases come from group 1 and group 2 on the periodic table. Things like sodium hydroxide, potassium hydroxide. Basically group 1 is the alkali metals, group 2 is the alkaline earth metals. And really, if we talk about something being basic, it's basically referred to as being alkaline. So hence the name where they kind of come from. Alkaline really means basic. And that again is our group 1 and group 2 there on the periodic table. And that's definitely where a lot of strong bases come from. Pretty much if you look at the periodic table, you got like sodium, potassium, you hang a right over there to calcium and strontium and all those guys. So like these guys here with OH in the formula typically will be your kind of strong bases. Now, one important thing, when we talk about sort of acids and bases, and especially in sort of acid-base chemistry, is the idea of two things that are very much sort of meaning the same thing. So an acid is really something that can produce H+ ions in solution. And these are also sometimes referred to as protons. And again, a reminder that hydrogen has a proton. It has an electron. It does not have a neutron. So when something becomes positive, it loses an electron, which leaves the hydrogen as being basically only a proton in that case, which is why it's named that. But in addition, in pretty much all of this chapter, and pretty much when you are dealing with acid-base chemistry, H+ and H3O+, this is what is referred to as the hydronium ion. They are, for all intents purposes, the same. So you will see when I write formulas or when I write equations, sometimes, people will use H+ and sometimes people will use H3O+. And there really is a reason why there's a difference in those two things. But in terms of the meaning, in terms of acid and bases, H+ is equivalent to H3O+. So keep that in mind as we go through this chapter. Anywhere you see me write an H+, you pretty much could write an H3O+ and vice versa. So they really do mean sort of the same thing. They do represent really the acidic part of a solution. So both in formulas and both in equations, you basically could substitute those two things out. An acid, again, is something that's able to produce H+ ions in solution. When we're talking about that, we're talking about the ability to produce free H+ ions in solution floating around. So, that's basically what an acid can do, is that ability. And there's certain strong acids. There's some strong acids like hydrochloric acid, nitric acid, sulfuric acid. So some of these strong acids, just kind of like a little list: hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, hydroiodic acid. So these are all strong acids, which means when they are in solution, for example, if you had some nitric acid there, in solution, they will break apart into H+ and NO3-. And these guys this is a strong acid, which means it's really a strong electrolyte like we talked about. And if you remember, electrolytes, especially strong electrolytes, will 100% break apart in solution, which means in that solution, you have 100% those ions floating around. You have zilch of those guys, none of these. I guess I'll write none instead of 0. None of these guys in solution. They have all completely broken apart. And that's really why it's considered a strong acid, because essentially when something like nitric acid goes for a swim, it produces a lot of free H+ in that solution very, very quickly. And that makes it a very strong sort of acid. Any questions on that there? Now, we'll take a second here just so you understand, how to name acids sort of correctly, in case you obviously come across them. It's good to understand, sort of where the names. So let me just give you kind of the Cliff Note version of how to name acids. So for example, acids in terms of naming really all involves basically oxygen and whether or not the acid has oxygen in it. So if the answer is no oxygen, then the acid name starts with hydro something ic acid. So for example, that's why when we go HCl, this is an acid. By the way, I know it's an acid because it does say aqueous next to it, and that's usually what acids are. And we see no oxygen, so this becomes hydro, and the negative guy here is chloric acid. So this would be hydrochloric acid. The cation in this case, if you remember, the positively charged ion is actually H plus, and the anion is Cl minus. Every single acid you deal with, the positive guy is always H plus, and the negative guy there as well. That's also why, you know, we have something like HBr, that's an acid. No oxygen in the formula, so this would be hydro, the Br part is the next part, bromic acid. So it is really only the oxygens that do not have oxygen that get the hydro part of the name. People, when they name acids, like to use hydro on everything, but it actually goes for special types of acids that do not have oxygen. If the answer is yes, that it does have oxygen, these are sometimes referred to as oxy acids because they have oxygen. And if it does, it will contain one of those polyatomic ions, if you remember from naming. And if you remember from naming, polyatomic ions end in ate or ite, right? Most of them. And if the answer is yes, and your polyatomic ion ends in ate, the acid would be something ic acid. So for example, HNO3. NO3, it has oxygen. NO3 is NO3 minus, which is nitrate, which means this acid name would be nitric acid. Just like if you had H2SO4, SO4 here is really SO4 2 minus, which is sulfate, which means this guy becomes sulfuric acid. Now you may be wondering why there's two H's here, and that's because the cation is positive, which means you need two H pluses to balance out the -2 charge here of the sulfate. So again, that's why there's two H's in that case. And lastly, you know, if you're naming acids and your polyatomic ion ends in ite, the acid is something OUS acid. So for example, HNO2, NO2 here is NO2 minus, which is nitrite, ITE. This then becomes nitrous acid. Again, no hydro or any of those. So any acid that has oxygen should not have hydro in the name. And if it does have oxygen, it's based on the polyatomic ion, whether or not that ends in ate or ite. Any questions on the Cliff Note way of naming acids? That way, at least you could name the acid instead of, you know, that thing there, right? All right, so let's talk a little bit about bases then. Bases, on the other hand, as I mentioned, are things that produce hydroxide in solution. And very much like the acid, in order for something to be a base, what we're talking about is the ability to, when it goes for a swim, basically produce free OH minus ions, basically hydroxide ions, basically flying around. And as I mentioned, there are several strong bases, which are strong electrolytes. And again, as I wrote on the other side there on the periodic table, group 1 and 2, sodium, potassium, calcium, and again, kind of coming this way, any of these guys with hydroxide in the formula are typically your strong bases. And the same thing as an acid, a strong base is a strong electrolyte, which means it will 100% break apart into ions. As we see here, this should be plus. There we go. So if we have sodium hydroxide in solution, sodium hydroxide again will not stay together. It will 100% break apart into these ions. So much like our strong acid, this is 100% of what you have. And as you can see here, produces a lot of OH minus, which is why it's a strong base. Same thing with KOH, which is potassium hydroxide, breaks apart 100% into potassium ions and hydroxide ions. Again, 100% of what you got in that solution is this guy. You have none of the KOH solutions still together, also producing a lot of OH minus very quickly, which is why, again, it's considered a strong base. Any questions on that there? So let's talk about some reactions that occur between a strong acid and a strong base. The fundamental change that occurs when we take a strong acid with a strong base is really the formation of water. And that's why it's sometimes referred to as an acid-base neutralization reaction. So when we do take a strong acid and a strong base together, there's basically a double displacement reaction happening. So for example, if we took hydrochloric acid plus sodium hydroxide, that is a strong acid and a strong base. And again, if you look at this, this is a positive, negative guy, positive, negative guy. This is really a double displacement reaction, which means that the H plus from the acid will switch partners and end up with the OH minus from the base. And that is basically where water is formed from. And we make a salt, which is what is left over. So this is water and a salt. And that is pretty much always made when you take a combination of a strong acid and strong base together. You make water and you make salt. The water part always coming from H plus from the acid, OH minus from the base, and then obviously our salt part here coming from these ions coming together correctly. +1 and -1 is essentially where these guys come from. So it doesn't matter sort of what combination that you make when you have an acid and base. Really just take the water out and then put the other guys together sort of correctly. A salt really is just an ionic compound. So it's basically a positive cation and anion together. So what is happening in this equation? Well, if we really look at sort of what is happening in the solution when we put these guys together, you know, if we take these guys and basically dump them into a beaker, big beaker, they basically, because this is a strong electrolyte and this guy's a strong electrolyte, they basically will break apart. And we basically will have H pluses floating around, Cl minuses floating around, sodium ions floating around, and hydroxide ions floating around in that particular solution. And what's going to happen is when that H plus and that OH minus sort of see each other, there is a very strong attraction between these two guys. And they will come together basically to make water. And what we end up with is obviously the formation of water. And we still have the other ions basically floating around. They're what are referred to as spectator ions. They're just kind of hanging out and watching, but these guys are still floating around and we do make water. And you may remember that one of the sort of driving forces for why a reaction takes place is actually the formation of water. So that's really one of the reasons why a reaction will take place. Here, honestly, if you did this visually, you pretty much won't see much happening because, you know, you made water, so you can't really see it. It's unlike, for example, a precipitation reaction where you would see a solid formed or anything like that. But we are still making water, even though, you know, visually you might not be able to really sort of see that occur. But that really is, you know, the ultimate thing that's happening here is what we see down here. Sort of sometimes referred to as a net ionic equation. The net ionic equation basically tells you in a reaction pretty much down to the basics of what is happening. And what is happening is, as we can see up here, the H plus from the acid, the OH minus from the base, are coming together basically to make water. So these guys are basically coming together to form water. And that's ultimately what is happening in pretty much any combination of a strong acid and strong base. Remember, it really is just a double displacement reaction as well. And most of the time, the salt is soluble. So in each of these cases, strong acid, strong base, water, and a salt. This again, a strong acid, strong base, water, and a salt is basically formed. Now, if you had something like sulfuric acid here, and you reacted it with sodium hydroxide, again, positive, negative. Same thing going to happen is going to be our H from the acid coming together here with our OH from the base, and that is going to make our water. What is left, if we really just sort of look at this, is we have sodium ion that's left over at this point. So we basically have the sodium ion, and we really have the sulfate ion here. So when these guys come together to make our salt, we want to put it together like a normal ionic compound, just like we did with nomenclature. That means we need not one sodium, but we do need two sodiums to balance it out. And our salt should look something like this. And obviously that would be our salt in this case. This equation is not balanced, which means you need probably a 2 there and maybe a 2 there. And I think that might balance it. So we're balanced at that point. So again, water here and a salt is made from a combination of a strong acid and strong base, where pretty much 100% of the time, the H plus comes from the acid, OH minus comes from the base. Any questions on that there? So let's talk a little bit about, again, some definitions or early sort of definitions of acid and bases. Arrhenius, he was first person to sort of recognize sort of the nature of acid and bases. He did a lot of work with electrolytes. He defined an acid as something that's able to produce hydrogen ions in solution. So again, basically what that means is it has to be something that's able to, in solution, produce H plus ions floating around, or again, because they are interchangeable, H3O plus ions basically floating around. Again, they basically represent the same thing. He defined basically a base as something that can produce hydroxide ions in solution. And same idea as we talked about previously. What that means is, again, in solution, we got a bunch of these free OH minuses basically floating around. So, for example, if we take some hydrogen chloride gas and we put it into sort of water, we get hydrochloric acid. And that's the difference between, say, HCl that's a gas, which we would call hydrogen chloride gas, versus HCl that is aqueous, which would be hydrochloric acid. Again, the acid. The aqueous part means solution. Aqueous part means we got these guys floating around in the solution. This guy obviously is a gas at that point, which means they're still together. They haven't really broken apart. And that's why typically we do see the aqueous symbol written next to acids to indicate sort of the difference between, are we talking about the gas form or really the acidic form or acid form? Same thing here. We take some solid sodium chloride, dissolve it in water. We do get, again, those free sodium ions, which really is not important in terms of acidity or anything like that, but we do get a lot of free OH minuses that are basically floating around. Now, Arrhenius had a pretty good sort of definition, if you will, or concept of acid and bases. It was limited because he did a lot of work with electrolytes, and he focused in on a lot of bases that contain hydroxide. And really not all bases have actually hydroxide in their formula. So for example, most strong bases do have hydroxide or OH minus in the actual formula, like sodium hydroxide, like potassium hydroxide. But there are some bases which are actually like weak bases, for example. So for example, there is a weak base, which is ammonia, NH3. And NH3 is a weak base. It does not have any OH minus in the formula. But something like NH3 has the ability, as we will see sort of in this chapter, to go and react with water, for example. And in that process, what ends up happening is the NH3 will actually pick up an H plus and make NH4 plus and OH minus. So because the NH3 is able to react with water and produce, bad arrow there, try that again, fix the arrow. Because it's able to produce hydroxide, it is still considered a base. It is a weak base because it pretty much has to go and do a reaction to generate the OH minus. And that's different than, say, a strong base, which pretty much, like sodium hydroxide, all it has to do is go for a swim, and it's basically carrying, if you will, its own hydroxide. So it's got its own hydroxide on board. So when it goes for a swim, boom, we sort of automatically produce a lot of OH minus really quickly. Why it's a strong base compared to something like ammonia, which has to go find the water, do a little reaction to produce some hydroxide. So, there are definitely bases that do not contain OH minus in it. Most of them will probably be more on the weaker side in terms of a weak base, but they're still considered bases because they have the ability to still produce OH minus. Any questions on that there? So moving sort of forward from the Arrhenius definition of an acid and base comes to really definition of acid and bases that we most often sort of look at and sort of discuss. Whoops, and that is not the wrong button. Try that again. There you go. That was the right button there. Okay, so we have what is known as the Bronsted-Lowry definition of an acid and base. And the Bronsted-Lowry definition of an acid and base, the Bronsted acid is a proton donor, and the base is a proton acceptor. By the way, when you do see HA written like this is like a generic version of what is referred to as a monoprotic acid. It's monoprotic because it has one H to give, mono meaning one, protic meaning proton. So it has one proton basically to donate. And again, the generic guy here would be like H plus and A minus in this case. This is kind of like HCl, right? H plus and Cl minus is basically an example of like HA. Now, when we do this sort of relationship, this Bronsted-Lowry relationship, as we sort of see here on the bottom, what ends up happening is because this is an acid, this guy right here is our acid, it will end up donating its proton to water in this case. And since water is accepting the proton, water in this case is acting as a base. It's really important when we talk about these things that it is not just a hydrogen that's being transferred, but it is an H plus. The plus does affect the overall charge of things. When you gain a positive, you become one more positive. When you lose something that's positive, you become one more negative. And that's what we see over here. We see things that are basically related to each other. So when that acid, that HA, donates its H plus over, it becomes A minus on the right-hand side. And A minus is its what is known as its conjugate base. Just like water, though, when water sort of accepts the H plus, water here then becomes H3O plus. And since this is the base, this would be what is referred to as the conjugate acid. So these two guys are related to each other as the conjugate acid. So we create what are referred to as conjugate acid-base pairs. And there's a couple of things that's important to remember when you look at these. First off, your regular run-of-the-mill acid and base are always found on the left-hand side of the arrow. Your conjugate acid and your conjugate base are always found on the right-hand side of the arrow. And the relationship between each of these guys is a really important one to understand. It is that relationship right there, only a difference of 1 H plus. So for example, if we look at the guy on the bottom there, between HA and A minus, between the acid and its conjugate base, the difference is 1 less H plus. Between water and H3O plus, the difference is 1 more H plus. The difference between these guys on the other side, only difference there can be is 1 H plus only. So that's a really important thing to remember if you're trying to determine if something is an acid conjugate base pair are related to each other. That has to be the only difference that you see is just 1 H plus. Any questions on that there? So if we look at, sort of a real example like HCl and water. In this case, obviously, this right here is our acid. It's going to donate again to water here that's acting as the base. The result of that is we get a combination of the acid losing its H plus, which now means on the other side, that is his conjugate base, while the H2O gains the H plus, and that becomes his conjugate acid in this particular case. So we get these guys again related to each other, this guy here and this guy related to each other. Again, the difference is 1 less H plus, and we also see this guy here and this guy here are related to each other. And again, the only difference is 1 H plus, and it can only be really 1 H plus at a time. If there's any difference between the two things that's greater than 1 H plus, or there's other elements that are different, then they are not related to each other as conjugate base pairs. Any questions on that there? So what's happening here, as you can see, again, is that HCl is donating its H plus over to the water, and that makes our H3O plus and our Cl minus. So earlier I mentioned that, in acid-base chemistry, H plus is pretty much the exact same thing as H3O plus. And really the difference in terms of whether or not you get sort of H plus or H3O plus, sort of in your equation has really to do with whether or not you sort of include water. So for example, what we're really looking at here is what's referred to as the dissociation of an acid, which is a fancy way of saying it breaks apart. And if we take hydrochloric acid, which is a strong acid, we could represent it breaking apart by simply writing H plus and Cl minus. We could also show hydrochloric acid breaking apart by including water in that reaction, which would be H2O. Where we look at it more of a traditional Bronsted-Lowry relationship, where this guy is going to donate its H plus over. The result of that is we end up with Cl minus and H3O plus. And both of these reactions, this one and this one, they basically represent the exact same thing. The only difference is if you use water in the equation, like we did here, you will end up with H3O+. If you don't use water, like no water in the equation, you'll end up with H+. And again, both of these guys here and here are the same thing, basically represented. Personally, when I write the reactions, I probably will write it like this top version. But again, you can replace the top version with the bottom version. Basically means the same thing. So any questions on it there? All right, so let's take a look here. What we want to know is in each of these cases, 1, 2, 3, and 4, are 1 a acid conjugate base pair, are 2 an acid conjugate base pair, is the pairing there in 3, and is the pairing in 4. So take a second and see what you come up with. We're looking for which ones meet the definition of an acid conjugate base pair. And remember sort of what that means, what we just talked about. Let's talk about really how we can determine if they are acid conjugate base pairs or just conjugate base pairs here. The first most important thing is to remember what we were just talking about, which means the only difference that you should have if these guys are related to each other is 1H+. So again, that is the only difference that you could have between them in order for them to be related to each other. So if we look at number 1, for example, we have HClO4 and ClO4 minus. So first off, the most important thing we want to look at is, are they related to each other? And it does look like they're related to each other. And what is the difference between these two? And if we look, the difference between these two is just 1H+. You can see that by taking away the H+ here. When you take away the H, you're left with ClO4. And again, when you take away the positive, you become one more negative, which is what you have on the other side. Or you could just add the H+ to the guy on the right, you get the guy on the left. So because number 1 here, the only difference is 1H+, that guy would be, or those two would be a acid base pair, conjugate acid base pair. Any questions on that one there? Looking at number 2, we have HCl and ClO minus. So the difference here is 1H+, but in this particular case, we also have a difference of O here and no O here. So nothing there in terms of the O. So there's also a difference of 1 oxygen difference between these two, which is no good. That means that these guys are not related to each other and they are not a pair in this case. So again, the only thing that can be different is 1H+. If we look at H2PO4 minus and HPO4 2 minus, again, if we look at these two things, the only difference going from left to right there is 1H+ less. So again, if I kind of subtract, for example, the H+ out of here, first off, if I take the H, I'm left with HPO4 minus. And if I take the plus off of it, I become one more negative, which would be HPO4 2 minus, which is the same thing that I see over here. So these two guys are related to each other, and they would be a conjugate acid base pair. Lastly here, looking at the relationship between these two, really the only difference is 1H+ left. Again, if we kind of take the H off of this guy, we're left with NO3. And then we take the plus, we become one more negative, NO3 minus, which is exactly what we got going on here. So these guys would be conjugate acid base pairs. Any questions on that one there? So let's try a few more here. So for each of these, write the conjugate base for each of them. So take a minute or two, see what you come up with, but we're looking for, starting with each of these, the conjugate base for each of those guys. Again, should only really be a difference of an H plus. So see what you come up with. Okay, so we want the conjugate base for each of these. And sometimes, when you're given a problem like this and they ask you write the conjugate base or write the conjugate acid, sometimes it's really important to sort of think about things sort of backwards in the sense of where it came from. And what I mean by that is we know, generically speaking, if we have an equation, it's acid plus a base. And then on the other side of the arrow, we have our conjugate acid plus our conjugate base. And the relationship between those guys is the acids on the left makes a conjugate base. And the base on the left there makes a conjugate acid. So those are the relationships between them. And, really, as I mentioned, the only thing that you should do is something with 1H plus. The key is here, should you add it on or should you take off the H plus? So when we think about what we're asked for here, which is what is the conjugate base, we know that we are looking to find the conjugate base here, which means if we kind of follow the path back to its origin, we see that pretty much everybody here would then have to be an acid because we're trying to write the conjugate base. So that tells us it's an acid. And we could use the basic definition of what an acid is, which means it's going to donate an H plus, while a base would accept, obviously, an H plus. So by thinking about it sort of backwards, if you will, where it came from, we know each of these guys should basically donate an H plus, which means the conjugate base would have one H plus less than what it started with. Any questions on that there? That means if we look at the first one here, we should take away the H, which leaves us an H and an S. And again, we're not just taking away the H, but we are taking away the positive. So when we take away the positive, we become one more negative, and we end up with HS minus. Same thing here for the second one. We're going to remove an H. So when we remove an H, we end up with an S. We also are removing the positive, which means we become one more negative. It's already -1. So one more negative would be -2 in this case. Any questions on those first two? Same thing here. We're going to take away the H, which leaves us an N, H, and 2. Took away an H. Also, again, taking away the positive, which means we become one more negative, which would be NH2 plus, NH2 minus. And lastly here, we're going to take away an H. That's still going to leave us an H. HSO3, again, no charge here, which means we will take away the positive and become one more negative here. So these would be the conjugate base for each of these guys. Any question on those? Again, the difference between each of these is just one H plus, which is definitely what it should be. Any questions on that there? So once you try this one, why don't we do HCO3 minus. Let's do the conjugate acid. And let's do on this side the conjugate base. All right, so take a moment or two, and starting with this guy in the middle, write the conjugate acid, and then write what the conjugate base would be. So we'll go this way first. We're looking for the conjugate acid. So in this case, we could do the same thing. I'm looking to find the conjugate acid, which means in this case, going backwards, what I am starting with is a base, and the definition of a base is something that should accept an H+. So as we go from the guy in the center to the conjugate acid, we actually should add on an H+. And that means if we add an H to that, we get H2CO3 plus 1 and minus 1 equals 0. And that would be the conjugate acid for that guy. Any questions on that one there? Going from the guy in the center to do our conjugate base is the same thing as the example here. We want the conjugate base, again, working our way backwards here. That means that what we are starting with in this case is an acid, which means it will donate an H+. So same idea, we should take the H away. That makes us CO3 minus, and one more minus makes us a -2, which is carbonate, which would be the acid here. I'm sorry, conjugate base here. Now you may notice that this guy here in this particular case could act as an acid or a base. And there are certain things that actually do have that ability to act as an acid or a base. And those guys are what are referred to as being amphoteric. So an amphoteric substance is a substance that can act as an acid or base. Very commonly seen when you're dealing with something like what we're dealing with in the middle, when you're dealing with somebody that has like an H and also like a minus charge. It's a very common thing that they could actually go both ways. They could either act in certain cases as an acid and in other cases also as a base. Any questions on how to identify acid conjugate base pairs? Obviously, you need to be able to do that. You need to be able to identify the acid, the base, and identify as conjugate acid and conjugate base pairs. Any questions on that there? Okay, then let's talk about acid strength a little bit. So when we talk about sort of acids, there really are a couple of different types of acids. There's really the strong acids, and there's really, the weak acids, if you will. And in a place where we do get these arrows heading in both directions, again, a reminder, this means that this reaction is reversible and there is a forward direction where people are going to. And if they're coming back the other way, there is a reverse direction that's happening here. We also could tell that this here would be a weak acid, really because of these arrows. The arrows really do indicate that reversible reaction, and that is typically what we see in the case of a weak acid. A weak acid is a weak electrolyte, which means, again, it will basically stay together in solution, but still be able to produce a little bit of H+ or H3O+, so it's still considered an acid. So if the forward direction predominates, we do have a strong acid. And again, I mentioned some of those strong acids earlier here, but again, for something like hydrochloric acid, it is really just a one-way street where it breaks apart into H+ and Cl-. Again, 100% what you got going on is this guy. None of these guys still there in the solution. And really why this is considered a strong acid, as I mentioned before, all it has to do is go for a swim. It's going to produce a lot of H+ very, very quickly and be what is referred to as being completely ionized or completely dissociated, which is basically a couple of fancy words for saying it completely breaks apart into ions in solution. And again, as I mentioned, just visually, if you were to put that hydrochloric acid in solution, you get a ton of H+ and also Cl- floating around. But because you have a lot of these H pluses, again, that's going to be a strong acid in that particular case. If the reverse reaction sort of predominates, you will get a weak acid, which again will basically be represented by those arrows. So for example, if you took hydrofluoric acid, which is a weak acid, it would also break apart into H plus and F minus. One of the major differences here is if you put hydrofluoric acid into a beaker, because it's a weak acid, it's a weak electrolyte, what you mainly have in solution is actually the HF guys floating around. So you mainly have these HF guys floating around. So this is mainly what you have in that solution. You have a little bit of these guys here. Try again, a little of these guys. I want to write in that corner for some reason. Okay. So you got a little bit of these ions floating around. So in addition to the HFs that you have, you do produce a little bit of H plus and F minus floating around. So because it still has the ability to produce H plus, even though much less than a strong acid would, it's still considered an acid, but obviously nowhere near as strong as something like hydrochloric acid, which just completely produces H pluses because it breaks apart. HF, hydrofluoric acid, will stay together. Something like acetic acid is also a weak acid, and a weak electrolyte will mainly stay together. Any questions on that there? Now, a strong acid does contain a relatively weak conjugate base, and there is sort of a relationship, excuse me, there is sort of a relationship in terms of the acid and its conjugate base. And it's basically an opposite relationship. And what that means is if you're starting with a strong acid, its conjugate base will be relatively weak. And basically what that means in most cases is it will not continue to react with water and kind of mess up the acidity of the solution. If your acid is a weak acid, its conjugate base will be relatively strong. So there's sort of an opposite relationship between those things. Same thing with the base and its conjugate acid. If you have a strong base, you will end up with a weak conjugate acid. And if you have a weak base, you will end up with a strong conjugate acid. So there definitely is sort of the opposite relationship. Now, there are certain acids, again, there are strong acids, and I think I listed most of these on the other slide. But again, HBr, which is hydrobromic, you could add to that, hydroiodic acid, also some strong acids. Now, there are certain acids that can actually donate 2 protons, and there's some that could only donate 1. Something like HCl has basically 1 proton, or H, and this is what is referred to as being a monoprotic acid. Something like H2SO4, as we see on the bottom there, has 2 hydrogens, and they're referred to as being diprotic acid. Diprotic meaning it's got 2 H pluses to give. And you could have something like H3PO4, which is phosphoric acid, has 3 H's to donate, which is a triprotic acid. So when something has more than 1 H plus to donate, they actually do come off actually one at a time. So sometimes people think, oh, well, it's got 2 H's and they all come off at once. And sometimes we sort of misleadingly write the reaction like this, like, hey, 2 H pluses and sulfate, for example. And, you know, this equation here is really the overall equation of what's happening in this process. And it sometimes causes confusion for people because people will look at it and go, okay, well, obviously this guy and these guys are related to each other because that is where it came from. So these guys are partners or bases, conjugate acid base pairs. And they're not, because there is basically two H plus difference. So these guys would not be pairs because the difference here is actually two H pluses. And really the reason why they're not pairs is the H pluses actually do come off basically one at a time. So if you took something like sulfuric acid, basically the first thing that would happen is this guy would basically lose one H plus, and you would end up with HSO4 minus. And then the next thing that happens is that HSO4 minus will then lose another H plus, and you end up with sulfate. And that is why when we look at something like sulfuric acid, it is a partner between this guy and this guy are partners. So they are partners. Again, the difference between those two is just one H plus. Also why when we look at this guy and this guy, they are also partners. The difference is one H plus. But when we jump from the first guy to the last guy there, this guy to this guy, they are not partners because, again, the difference is more than one H plus. So if we were to add these equations together, we get this overall equation here, which is, again, why sometimes people are confused by it. So again, only one H plus can be the difference if they are going to be basically related to each other. Any questions on that there? So water is an interesting thing. Water is an amphoteric substance, which means it could actually act as an acid or base. And here's a couple of examples I think we might have saw here throughout so far. In this first case here, the water is acting as the acid, which means it's going to donate its H plus over 10H3. The result of that is we get NH4 plus and OH minus in this case. That is our weak base sort of calculation. In the second case, the HCl is going to be the acid, going to donate to the base, in this case of water, the H plus, making our H3O plus and our Cl minus. Water can even act with itself. In one case, one of the waters is an acid. The other water, for example, is the base. And we would get that H plus transferring over to make our OH minus. And then obviously 2 hydrogens plus 1 more gives us H3 and O plus in that particular case. Now, when water reacts like this with itself, it sets up basically an equilibrium, which is why these are really two-way arrows. This is really arrows heading in both directions here. And it does set up this equilibrium where basically the rate of the forward reaction will equal the rate of the reverse reaction. And what that gives us is an important relationship in terms of acid and bases, and it is what is referred to as Kw. And that's basically the ion product of water. And it equals the concentration of H plus times the concentration of OH minus, and it equals 1 times 10 to the minus 14. Now, a couple of things here. We can absolutely change that out to H3O plus times OH minus equals 1 times 10 to the minus 14. Again, you can use either one, as H plus and H3O plus are the same. Now, an important thing is when we do the little bracket thing here, this represents concentration. And when we talk about concentration, we're really talking about molarity, which is moles per liter. And that's basically what we mean when we say that. There is a relationship between H plus and OH minus, and it's basically an opposite relationship, which means as the concentration of H plus increases, the concentration of OH minus goes down, kind of the acid part of the solution and the base part of the solution. And vice versa, if the H plus concentration goes down, the OH minus concentration basically goes up. We can use this to calculate the H plus concentration in a solution, and it's really the same calculation. If you want to know what the H plus concentration in the solution is, you take 1 times 10 to the minus 14 and you divide it by the OH minus concentration, and vice versa. If you want the OH minus concentration, you take 1 times 10 to the minus 14 and you divide it by the H plus concentration. Very, very, very important here is our calculator in this chapter. And a reminder that if you're going to push into your calculator 1 times 10 to the minus 14, you want to make sure that you use your exponent button here. And also want to make sure that you use your negative button. And obviously 14. Again, it should look something like this on a lot of people's calculators are or something like that. So definitely want to make sure you're using your exponent button here in this chapter for sure. Otherwise, you're going to be off. So let's take a look here. What does it mean if we do calculate the H plus and OH minus? Well, if we calculate the H plus concentration and it's larger, which means the acid part is larger than the base part of the solution, then the solution will be acidic. If we calculate that the OH minus part, which is the base part, is larger than the acid part, then the solution would be basic. And if the acid part and the base part are about equal to each other, it equals 1 times 10 to the minus 17, 1 times 10 to the minus 7, which means that it is a neutral solution. So definitely make sure exponent button here you are using on your calculator. So why don't we try some here, see what you come up with. So for each of these here, 4 different problems, calculate either the H plus or OH minus for each of the given and determine is it acidic, basic, or neutral. So again, these are 4 individual problems here. So it takes a few minutes here. You either need to come up with the H plus or the OH minus, and is it acidic, basic, or neutral? So for example, in the first one is the H plus concentration. I would need to calculate the OH minus concentration and compare the two and see which one's larger, and vice versa for all those guys there. So take a few minutes, see what you come up with. Again, make sure you use your exponent button, and we'll see if we all get the same numbers here in a second. Look and see. So again, take a look at the first one. So the first one gives us our H plus concentration. We're looking for the OH minus concentration. So KW is really what we want to use here. And we always have this sort of value. So that's the H plus concentration times the OH minus concentration. And again, it always equals 1 times 10 to the minus 14 in our case. In this case, they gave us the H plus, which means we are looking for the OH minus concentration. And really, it is the same calculation regardless of which one they give you. You're going to take 1 times 10 to the minus 14 and divide it by the other concentration, which means in this case, we would take 1 times 10 to the minus 14. We would then divide it by our H plus concentration in this case, which is 3.4 times 10 to the minus 4. Now, we do want to make sure that we do punch this in correctly on our calculator. So just to remind you, if you were going to punch this in, you would hit 1, you would hit your exponent button, which would put that E up. You would hit your negative button and you would type 14, and that would be the proper way to type that guy in. You then would hit your divide button, and then you would type the bottom guy in the same way. It would be 3.4, your exponent button, your negative button, and 4, and then obviously hit the equals button at that point. And if you do all that good stuff there, be good if I had a calculator around here. Let me see if I see 1 exponent button, negative 14. divided by 3.4 exponent button negative 4. Looks like you end up with 2.9 times 10 to the minus 11. And you do need molarity here as it is a concentration unit. That would represent the OH minus concentration. First off, any questions on that calculation there? Okay. So at this point, we've determined the OH minus concentration. We now want to determine, is it acidic, basic, or neutral? To do that, we want to compare both concentrations. We want to compare the H plus concentration, which in this case was 3.4 times 10 to the minus 4, to the OH minus concentration, which we just calculated at 2.9 times 10 to the minus 11. And hopefully in this case, if you look at these two numbers, you will see that the H plus concentration is greater than the OH minus concentration. So the acid part is larger than the base part. Now, sometimes people have a hard time understanding this part of it. So let me just explain it here. When we are dealing with negative exponents, like we are here, basically to the minus 4 to the minus 11, the negative is important here. It's actually the smaller number is the larger number. And why would that be? Well, what that means is, say the 2.9 number that we took to the minus 11 means we are going 11 places this way and putting zeros in front. For the 3.4 number, we're only going like 4 places this way and putting zeros in front. This is a much larger number than this guy, because once we place in our like 11 zeros, it's a much smaller. That's not, I didn't count, I just put zeros, but that's a much smaller number than say 4 zeros that we would put here. So the thing to remember is when you're comparing exponents that are negative, it's actually the smaller number is the larger number. So with negative exponents, smaller number, exponent number, smaller exponent number is the larger. Any questions on that there? Okay, so let's take a look at the rest of them here and see how we did. Maybe I got another page I could write on here, I think. Yeah. So the next one that we had was an H plus concentration of 2.6 times 10 to the minus 8. I think it's 8 molar. And that means that the OH minus would equal 1 times 10 to the minus 14 divided by 2.6 times 10 to the minus 8. Again, here we want to do our exponent button. So 1 exponent button negative 14 divided by 2.6 exponent button negative 8, and perhaps a 3.8 times 10 to the negative 7 molar in this case. Let me just grab real quick and make sure. So 1 exponent 14 divided by 2.6 exponent by negative 8. 3.8 to the minus 7 would be our hydroxide concentration. We're now going to compare the H plus, which is the acid part, minus 8, to the base part, which is minus 7. And in this case, the OH minus is actually larger than the H plus, which means that this guy would be basic, like the first one was acidic. Any questions on that one? Looking at the next one, which is the OH minus concentration is 6.2 times 10 to the minus 9, I believe. So it really is the same calculation. H plus would equal 1 times 10 to the minus 14 divided by this number. 6.2 times 10 to the minus 9. Again, we're making sure we use our exponent button here. And looks like if we punch it in, again, 1 exponent button negative 14 divided by 6.2 exponent button negative 9 gets us a 1.6 to the minus 6 as the H plus concentration. So remember, this is the acid part, this is the base part. So to the minus 6 is a larger number to the minus 9. So in this particular case, the H plus concentration is larger than the OH minus, which means the acid part is bigger than the base part. So we would expect this solution to be acidic. Any questions on that one there? And lastly, we have an OH minus concentration that is 8.1 times 10 to the minus 3. Rolling with the same calculations we previously did, H plus would then be 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. And punching that in again the same way as the others, 1 exponent button negative 14 divided by 8.1 exponent button negative 3. We end up with 1.2 to the negative 12. Again, we do need molarity there, just as a unit. Again, in this case, this is our acid part. This is our base part. The base is to the minus 3. The acid is to the minus 12. That means that the OH minus concentration is larger than the H plus, which means this guy should be basic. Any questions on any of those calculations? All right, I guess we will probably lay it up there for tonight in terms of lecture. Any questions on anything we talked about there?